Hello friends. Today, we will learn about another piece of equipment synonymous with the steel industry. It's called a blast furnace, which is the heart of any iron and steel plant. So let us know more about it. Disclaimer. The images used in this video are derived from open-source web search platforms. They are used strictly for educational purposes and are owned by their respective license holders. What is a blast furnace? A blast furnace is a critical component in the steel industry, used primarily for producing molten iron, pig iron, from iron ore, which is then further processed into steel. It is a tall, steel cylinder lined with refractory bricks designed to withstand extremely high temperatures, operating continuously for years until the lining wears out, and its maintenance is due. Next, we will learn about how a blast furnace works. The key steps involved in the operation of a blast furnace are: charging. For starters, iron ore, coke, and limestone are continuously added from the top section of the blast furnace in carefully controlled layers. Hot air blast. A blast of hot air, up to about 2,100 degrees Fahrenheit, or 1,150 degrees Celsius, is blown into the bottom of the furnace through tires, causing the coke to burn and generate intense heat, till 1,600 degrees Celsius or higher, within the furnace. Chemical reactions. Here, the coke particles react with oxygen to form carbon monoxide, which acts as a reducing agent, further removing oxygen from the iron ore, iron oxide, thus producing molten iron. Limestone reacts with impurities to form slag, which floats on top of the molten iron and is removed separately. Molten iron and slag removal. Molten iron is tapped from the bottom every hour or so, while slag is skimmed off and removed. The molten iron produced in the blast furnace is brittle and contains impurities, so it is sent to a basic oxygen furnace converter, where oxygen is blown in to remove unwanted elements, and convert it into steel. In this section, we will learn about the importance of refractory lining in blast furnace operations. The refractory lining of a blast furnace is a complex, multi-layered system, designed to protect the furnace shell from extremely high temperatures, abrasive materials, and chemical attacks during iron making. It ensures the furnace's durability, safety, and continuous qualitative operation. The blast furnace lining is made of refractory bricks, often magnesia, alumina, or other specialized materials, that protect the furnace shell from extreme heat and chemical attack, ensuring durability and efficiency. The purpose of refractory lining is to protect the steel shell from heat and abrasion, withstand chemical corrosion from molten iron, slag, and gases, and maintain structural integrity under thermal cycling. The refractory lining is actively cooled by stave coolers to prevent overheating and prolong lining life. Different parts of the blast furnace use specific refractory materials, tailored to the local conditions of temperature, chemical attack, and mechanical wear. Typical refractory materials by separate furnace zone can be accessed here in this table. The main materials used in the refractory lining of a blast furnace vary by furnace zone but generally include: high alumina bricks, 42 to 62% alumina. Used in critical zones such as Bosch, tire, tap hole, and lower hearth for their high refractoriness, mechanical strength, and resistance to chemical attack. Silicon carbide and its composites. Increasingly used in the belly, Bosch, tire, and tap hole areas due to superior abrasion resistance, thermal shock resistance, and chemical stability. These materials are often self-bonded or tar-bonded. Fireclay bricks, 39–42% alumina. Commonly used in the stack and belly zones to provide abrasion resistance and chemical stability at moderate temperatures. Often, Super Duty fireclay bricks are used in the stack. Carbon and graphite blocks. Widely used in the hearth and lower parts of the furnace due to their excellent resistance to molten iron and slag corrosion, high thermal conductivity, and thermal shock resistance. Corundum bricks, high purity alumina. Used in the belly and tire zones for high wear resistance and corrosion resistance. Mullite bricks. Often combined with high alumina bricks in the Bosch and tire zones for improved thermal shock resistance and corrosion resistance. Ceramic cup bricks. Plastic phase-bonded composite corundum bricks are used in the hearth bottom and tap hole areas for high refractoriness under load and corrosion resistance. In a nutshell, the refractory lining must resist abrasion from the burden materials charged from the top. It must withstand chemical attack from carbon monoxide gas, molten iron, slag, and alkalis. Thermal shock from temperature fluctuations and mechanical stresses are critical factors influencing lining life. Proper installation and maintenance, including cooling systems, are vital to maximize lining life. We have reached the shutdown maintenance part of the blast furnace, so let us proceed. Shutdown maintenance of a blast furnace is a complex, carefully controlled process essential for ensuring safety, preserving furnace integrity, and enabling repairs or relining. The procedure can take several weeks, and involves multiple steps to safely cool down, empty, and maintain the furnace. There are different stages of maintenance, which are carried out as follows. First is preparation phase. Stabilize furnace operation. In the 8 hours leading up to shutdown, adjust furnace temperature and slag basicity to optimal values to improve slag and iron mobility, and reduce the risk of accretions. Normal stockline operation. Maintain the stock line and begin filling the descending space with a mixture of coke and coke nuts, typically in a 2:1 ratio, to support clean-out and later recovery. This helps clean the furnace walls, and enables efficient removal of residual materials. Inspection and cooling preparations. Inspect cooling systems, ensure water fetching devices are operational, and prepare for possible overflow checks. The second phase is blow-down, blow-out operation. Cease charging. Charging new burden materials into the furnace is top. Allow the existing charge to descend naturally as it is consumed. Monitor stock movement. Watch for abnormal drops in the stock line, which may indicate air infiltration or excessive coke consumption. Apply sealing sprays if needed to prevent air ingress. Maintain blast. Continue normal blast operation initially, then gradually reduce, and finally stop the hot blast as the charge level lowers. Residual iron and slag removal. As the coke and coke nuts descend to the tire level, stop the wind, blast, and begin draining residual iron and slag. Early in this process, the stock column's weight helps push out molten iron. As the flow decreases, introduce cold air to accelerate cooling and removal. Bleeder valves and gas handling. Open bleeder valves as needed to safely vent gases. Purge the furnace and gas cleaning sections with steam or nitrogen to prevent explosive gas mixtures. Third phase is furnace cooling. Plug tires. Once residual iron is removed, plug all tires to prevent air ingress. Apply water granulated slag. Add a layer, about 60 cm thick, of water granulated slag on the material surface to protect the lining and further cool the furnace. Water fetching and overflow. Use the furnace roof water fetching device or overflow, cooling water to cool the furnace roof and other critical areas. Reduce cooling water gradually. For extended outages, reduce water flow to cooling members over several weeks, maintaining only hearth stave cooling as needed. Final steps and maintenance access. Open furnace top. After the furnace has cooled sufficiently, open the manhole at the top for inspection and maintenance access. Daily inspection. Continue daily checks of the stocking and cooling systems. Address any abnormal stock movement or temperature rise immediately. Safe entry. Only after the furnace is confirmed to be gas-free and adequately cooled can personnel enter for relining, repairs, or detailed inspection. Some key considerations to be kept in mind during the maintenance activity are: safety. Purging with inert gases and careful venting are critical to prevent explosions due to residual combustible gases. Environmental control. Proper handling of gases and dust emissions during shutdown is necessary to minimize environmental impact. Resource recovery. Coke and coke nuts used to fill the furnace can often be recovered and reused after maintenance. Duration. A full shutdown and maintenance cycle can take several weeks, depending on the scope of work and cooling requirements. This procedure ensures a controlled, safe, and efficient shutdown, minimizing risks to equipment and personnel while preparing the blast furnace for maintenance or relining. What are the latest developments in the blast furnace maintenance domain? AI and vision systems. Advanced AI and computer vision now enable real-time monitoring of raw material size, burden distribution, and refractory wear, allowing early detection of issues and predictive maintenance, minimizing unexpected shutdowns and improving efficiency. Digital twins and condition monitoring. Digital twin technology and smart sensors provide continuous data-driven insights, enabling predictive and condition-based maintenance instead of scheduled replacements, reducing costs and downtime. High-performance refractories. Innovations such as magnesia carbon blocks and silicon carbide linings allow faster repairs and greater resistance to extreme furnace conditions, extending campaign life and reducing maintenance frequency. Automation and modernization. Upgrades like bell-less top charging systems, improved access for maintenance, and automated process controls streamline maintenance, reduce manual intervention, and enhance safety. Integrated digital platforms. Platforms that unify monitoring, diagnostics, and forecasting help optimize maintenance schedules, support decision-making, and lower operational costs. These advancements collectively boost blast furnace reliability, efficiency, and sustainability while reducing maintenance costs and environmental impact. Techniques like spray repair, gunning, grouting, and remote-controlled or robotic repairs minimize downtime and avoid full shutdowns, unlike standard equipment maintenance, which typically relies on scheduled preventive or corrective actions. In summary, blast furnace maintenance is more complex, risk-sensitive, and costly than typical equipment maintenance, requiring specialized methods to address the unique operational and safety challenges of continuous, high-temperature iron making. At this stage, we will conclude with this video and would like to thank you all for taking out your valuable time to learn about this topic. We shall meet again shortly with another informative video on another industry equipment. Do post your comments and feedback in the comment section. Have a great day ahead, and follow our blog for more informative posts.